All right, so this lesson is about alkynes and aromatics. We learn about alkanes and alkenes, okay, single and double bonds. So alkynes would be triple bonds. We're just going to be learning how to name triple bonds, how they react, and how to draw triple bonds. And then we'll talk about aromatics, okay, and learning how to name aromatics as well as reactions. So before we can jump in, let's do a review. Let's name these three structures that contain double bonds, okay? You need to know how to name a double bond in order to learn how to name a triple bond because they're very similar. So I'll give you 3 minutes and I'll take these ones up. All right, so for the first one is actually very simple. You have 5 carbons in the longest chain, and you must contain the double bond, so you have 1 methyl group. And obviously you will count from the right side, having a 1 on the double bond, so it's 4-methylpent-1-ene. Okay, I hope you all got this one. The next one, though, is a lot more complicated because it has a ring. So can somebody tell me which one is carbon number 1?
The one between chlorine and double bond.
So the one above the chlorine?
Yeah.
Are you sure?
No.
No? Who's sure? You guys agree with that answer, the one above chlorine? Or do you have a better answer? Nobody? Well, if you choose the one above chlorine, which one would be carbon 2?
Oh, right.
The carbon on top of chlorine, that's carbon 1. Which one will be carbon 2? The one with the chlorine?
The one with the chlorine.
So not across the double bond, not with the one with the double bond. So you choose the one on top of chlorine as 1, and then you go down to chlorine as 2. All right, I see what you're saying. That would give you a pretty small number. And you did make the double bond 1. So it seems like you satisfied everything. But you have to make sure that you count across the double bond. All right, so once you pick a carbon to be 1 and it has a double bond, you must count the other carbon with a double bond to be 2. You can't go in the other direction. All right, so the best answer is this. That being carbon number 1. So 3-chloro, 6-methyl, cyclohexone. So that would be 2. This one will be 3. This one will be 4. That will be 5, and that will be 6. All right, now why is this the best one? What is wrong with picking the carbon on top of chlorine to be number 1? All right, so why can't you do this? 1, right? And 2, 3, 4, 5, 6. Isn't that equally good? I picked that one, the one above chlorine. So that's 1. So my double bond has the lowest number. And also, I have a 3-methyl and a 6-chloro. So that is the smallest set of numbers. Okay, they're tied, in fact. The way that I labeled it, the top carbon being carbon 1, the one above chlorine being carbon number 2, I also get a 3 and a 6, okay, as my substituents. They are not equally good. Only one answer exists. Okay, whenever you see a tie, there must be a tiebreaker. So the one I labeled on the outside, that one is better because when you have a 3 and the 6, I want my chlorine to be the 3, my methyl to be the 6, because chlorine begins with C. It comes earlier in the alphabet. Does that make sense? Methyl starts with M, that comes later in the alphabet, so I want that one to be 6. If you switch them around, the first two criteria are satisfied. The one being double bond has the lowest number. You have the smallest set of numbers. Cool. But alphabetical order dictates that chlorine must be 3, methyl must be 6. So this is the only answer. So make sure you are very careful when you have a ring and you decide to start somewhere. You have to know where to start and which direction do you count once you do start. So ring questions are a little bit more complicated than just normal structures. For the last one, you have 2 double bonds. All right, and obviously you count from the left side because you have a smaller set of numbers. And that will be the answer. You have 2Z for E. Okay, 2Z, the same side because the chlorine goes down. The rest of the molecule also points down. So same side. For E, well, the molecule is kind of like on opposite sides across the double bond at carbon 4. So that's why it's E. So 2-chloro, 3,4-dimethyl, hexa-2,4-diene. All right, make sure you know how to name double bonds. We're going to move on into triple bonds. Okay, any questions so far? Alrighty, so you've seen the slide before. Single bonds are alkanes. Alkanes have double bonds, so alkynes therefore would have triple bonds. How will we name that? Well, here are the naming rules. It is very similar to double bonds. First of all, you have to identify the parent, the one with the longest chain, or the ring. And that must contain the triple bond. You can't just omit the triple bond, okay? And if you name an alkyne, it ends with Y and E. And same as double bonds, if you have more than one triple, you have to add a suffix to tell me how many you have. So for example, diene or triene. And then next, you gotta number your carbon so that your triple bond has the lowest possible number. And you write this number before the suffix. Lastly, same as before, you name and number all the other substituents using the same rules, and you all put them together. Okay, so let's do some examples. So this is a simple one. There are 7 carbons in the longest chain. You can go from the left side or the right side. Which one do you choose, from the left or from the right? Oops. I can't hear you. Which one?
Wait.
The right?
The left side?
The left side. Why do I hear a lot of rights? You choose it from the left side. If you choose it from the right side, your branch has a 2, which is very low, but your triple bond will end up with a 4, and that will be bad. You want your triple bond to be as small as possible, so if you go from the left side, you would have a 3 for the triple bond. You don't care about the methyl group. Yeah, it has a 6, but you're not important. Okay, the triple bond takes priority, so you pick the one from the left side. Okay, you must ensure that the triple bond has the lowest possible number. So once you get that, well, that's hept-3-ine, because it's long carbon number 3. That's 6-methyl. You put that together. You get 6-methyl hept-3-ine. Okay, is this clear?
Yeah.
Basically the same thing as double bonds, okay? All right, so what if you have 2 triple bonds? With a question like this, again, you have to identify the longest chain. You have to include all of the triple bonds. And you can count from the left side or the right side. All right, and obviously one side is preferred over the other. it's very clear that if you count from the left side, you have the triple bonds 2 and 6. Whereas if you count from the right side, you have 4 and 8. And 2, 6 is smaller than 4, 8. We're going to count from the left side. And to name the parent, 10 carbons, you got 2. So that means deca 2,6-diene. Deca, you need the A. For the same reason you need the A for double bonds. When you have a C and a D, you better have a vowel in between. So deca-diene, not dec-diene. All right, so make sure you include the A. So once you're here, then you can just name all the branches. There's 4-chloro. There's 5-ethyl. There's 8-methyl. Another 8-methyl. And that's it. So alphabetically, C goes before E. E goes before M. Put this together. You have 4-chloro, 5-ethyl, 8,8-dimethyl, deca 2,6-diene. Okay, it just rolls off the tongue, doesn't it? It's nice and short. Notice that we didn't do isomers. There's no E, there's no Z. EZ isomerism applies only to alkenes, to double bonds. If you have a triple bond, you don't have that conundrum. Okay, the reason is triple bonds are linear. Notice that I drew my triple bonds in a straight line because the angle must be 180 degrees for a linear molecule. And if you're linear, there is no two sides. So obviously you wouldn't have EZ. Okay, so you don't have to worry about that. Does that make sense, everybody? Okay. Now, this is when I really hate you. Okay, you will see this on the test. But I don't hate you, so I won't put this on the test. At least I don't hate you yet. So this is just for practice. I just wanted to make sure that you know how to do a hard question like this so that you'll be able to handle the easier questions on the test. So let's try to do this one. I'll give you some time to work on this on your own. I'll give you a hint. If you have both double and triple bonds, they have the same priority. Okay, you don't take one over the other. So you still have to find the longest chain, make sure you have all the multiple bonds on it, and you have to name all of them. So I'll go ahead and attempt this one. I'll give you around 2 minutes. If you don't get it, that's fine, because this is new. And then I'll take it up. All right, so here goes. Okay, not this question, the next one. This one. First thing you do, you figure out the longest chain. The longest chain must contain all of the multiple bonds. So this is the longest chain. Now the problem is, where do we start counting? Okay, I know it is very tempting to start from the bottom because you have 2 chloros on carbon 1. You have a 1-1. That sounds very nice. But you have to give priority to the multiple bonds. If you count from the right, you have a 2 for the triple bond. So you have to count from the right. You have to take this set of numbers. So how would you name the parent, first of all? Okay, that's the hardest part. 9 for nona. 4,6-diene. 4 and 6, you have a double bond. 2-ine on carbon 2, you have a triple bond. See? You have to name both double and triple bond. Nona, not non, because N and D, you need to have a vowel in between. So nona-diene. Now, the diene dropped the E, if you notice. It was diene, now it's diene. Why did you drop the E? Same reason. Because now it follows Y and E. You can't have 2 vowels. Right? We consider Y to be a vowel in this case. So it's diene without the E and then ein. Okay, that sounds really weird, but that's how you would do both double and triple bonds. And you will write the double bonds before the triple bond because of alphabetical order. They have no priority over the other. So E comes before Y, you write the double first. That is the parent. Okay, after the parent, you have to figure out EZ. For carbon 4, this is E. Okay, they're on opposite sides. It's really easy to see that one points to the right, one points to the left. On carbon 6, they're on the same side. They both point to the right. So it's 4E6Z. And then finally, you can name the branches. That would be a 6-propyl. That would be a 7-methyl. That would be 8-methyl, 9-chloral, 9-chloral. Now you have all of this, putting them together alphabetically, C before M before P. And there you have it. You have 4E6Z, 9,9-dichloro, 7,8-dimethyl, 6-propyl, nona, 4,6-di-N-2-ine. Okay, very beautiful name. Any questions? Really, no questions. This is very intuitive. You got this. All right. So just make sure that when you name something with double and triple, you name them both. Okay, double is written before the triple. And you add a vowel or delete a vowel so that it always has consonant, vowel, consonant. Don't forget your EZ. Many people forget the EZ. Okay, and then you just name everything else normally. So that would be a hard problem. That would require a lot of time to do on a test. So don't expect something this complicated. So let's draw some alkynes. Here's an example. You've seen many examples of how alkynes should be drawn. So go ahead, try to draw this one. And again, I'll give you around 1 minute because that's a very simple alkyne to draw. Go ahead and draw this, and I'll take it up in 1 minute. All right, so you probably have something like this, right? Pent-2-ine, pent meaning 5. So you have 5 carbons in your longest chain. On carbon 4, you have a methyl. On carbon 2, you have a triple bond. This is the answer, isn't it?
Isn't it supposed to be straight?
Oh, yes. Thank you. Somebody didn't fall for it. I made a lot of money with this question. Okay, if we were in class, I will walk around to see who drew it like this, and then I'll ask them, do you think this is right? Usually the student looks at me and is like, yes. And then I'll be like, are you sure? And they will look at this, pause for like a few seconds, just double check. Well, I mean, I have the methyl. I counted the carbons right 5, and then triple bond is the carbon 2. Like, yep, no, I got this definitely. And then I say, do you want to bet? And they're so confident because this is a simple question, they don't see a mistake. They're like, yes, let's bet. So we bet $1. And then I show them, no, this is incorrect. And in fact, this is the answer. You're like, oh, crap. So I won many dollars by pulling this trick. I'm not trying to rip students off. I'm just trying to make them remember that you must have a linear triple bond. All right, this must be 180 degrees because of the Vesper geometry. There's no way to bend a triple bond because of the repulsion between the bond and the electron, so it must be linear. So if you bend the bond, you will lose marks. Okay, does that make sense? So please don't be tempted to do that. Yes?
Whenever you have a triple bond, you already have 4 carbons.
What do you mean?
Like, whenever you have a triple bond, you have at least 4 carbons.
No, you can have ethyne, literally 2 carbons triple bonded.
Oh.
Right, and to see, because you can't bend it now, how are you gonna tell the carbons apart? Very simple. Just draw the 2 lines, and where that 2 line end will be a carbon. You see how this works? So make sure you draw your triple bonds linearly. Okay? If you bend them, you're going to get it wrong. Double bonds must be bent. Okay? Single bonds must be bent because they have a bent angle. But triple bonds are linear. That's the key difference here. There are many textbooks. If you just Google something on the internet, you're going to see bent bonds, and those are all wrong. Okay, make sure it's linear. Okay, so that's the only trick with triple bonds. Just make sure when you draw them, it's linear. All right, so let's do some reactions. And like alkynes, they do addition reaction because they're missing a couple of bonds. Well, sorry, they're missing a couple of atoms. So that's why they have triple bonds. If you add, let's say, hydrogen in the picture with the hydrogenation reaction, the triple bond will break, okay? The first step is that you will form a double bond. Which type of double bond? It must be the cis isomer of the double bond. So an alkyne, with an addition, you'll become an alkene first. A cis alkene. It must be the cis because in nature only cis isomers exist. Trans isomers do not exist. And then after you get your alkene, further steps will then make it an alkane. Okay, so the net reaction will be an alkyne plus hydrogen. You just simply get an alkane. Does that make sense? You will do this until you are saturated. And you will need a catalyst and heat in order for this to happen because you need energy to break the bonds. Triple bonds are typically stable. You have to use energy to break it. And also, the Markovnikov rule can apply. In this case, it doesn't apply because those two carbons have equal hydrogen. But let's say one of the carbons has something other than hydrogen, then you will apply the Markovnikov rule. Okay, and if you are reacting with something that's not H2, let's say HCl, then you have to decide which one gets the hydrogen, which one gets the chlorine. Nothing changes from reactions of double bonds. So let's do this one. What compounds will be produced? Well, compounds or compound, it could be one, when bromine reacts with hex 2 ion. Okay, so you have to draw hex 2 ion first. You have to then use your drawing to predict the product, draw the product, and then you're done. So go ahead and attempt this one. I'll give you around a minute. You have to draw the intermediate, the alkene, as well as the final product, the alkane. Okay, so 2 minutes, please. So you will start by drawing hex 2 ion. All right, and that's quite simple. It's 6 carbon with just a triple bond. You don't have any branches. I drew it again with the hydrogens shown for more clarity. Okay, and you're adding bromine. So bromine is diatomic, so make sure you have Br2. What would this make? Well, the first thing that it will make will be an alkene. Okay, you break one bond, so now you have a double bond. So the alkene will look like that. Make sure that the bromines are on the same side because it must be a cis product. Okay, make sure that you bend the alkene. Alkenes are 120 degrees from each other. Okay, it's not linear anymore. From here, it will continue to react until it is saturated. So you will break the double bond and add 2 more bromines on it. You will look something like this. It doesn't have to look exactly like mine because I drew it with the program. If you decide to, just draw a straight line with 90-degree angles with the bromine, that's fine. That's just a Lewis diagram. All right, I drew it like this because the program, it's to display the hydrogens. Some students, they want to add the hydrogens. I don't know why. I prefer skeleton structure, but some students want to draw the additional hydrogens. For some reason, they count the hydrogens wrong. Okay, a carbon has 4 bonds and a hydrogen. I was like, oh, why did you do that? If you just omitted all the hydrogens, you would have gotten full marks. So I circle the hydrogen and I take off marks. So please, if you want to include hydrogens for some reason, make sure you count them correctly. A carbon must have only 4 bonds. All right, so first of all, any questions about this? Okay, so let's move on to the last little bit of today's lesson. And that will be aromatic hydrocarbons, okay? Aromatic hydrocarbons, what that means is you have a ring that has multiple double bonds in that ring. And then we'll be looking at the simplest aromatic hydrocarbon, and that will be benzene. We're not looking at any other ones. So benzene is C6H6. The structure of benzene has basically confused people for a long time. People knew that this existed. Okay, they knew this guy had 6 carbons and 6 hydrogens. They just didn't understand how that was possible. How can you have equal numbers of carbon and hydrogen? And until somebody figured out, hey, wait a minute, if you just arrange them like that, carbon with double bond in a ring, so 3 double bonds in a ring, and everybody has 1 hydrogen, you have C6H6, right? But hey, that's a great idea. So let's test this. Because double bonds are shorter than single bonds, okay, the bond length of multiple bonds are just shorter than single, you would expect benzene to have a crooked structure with 3 long bonds and 3 short bonds. And they measured the bond lengths of benzene. That is not what they observed. They observed that the hexagon of benzene is a perfect hexagon. All the bond lengths are exactly the same. Okay, that's weird. If you look at the structure of benzene, the simplified structure is the one on the right. You omit all the hydrogen, that's the skeleton. It looks like a sad face. You see alternating double bonds for a total of 3 double bonds, right? So shouldn't there be 3 short bonds and 3 long bonds? Actually, no, because benzene is able to display resonance. Okay, the proper way to draw benzene is not to draw 3 double bonds, because the electrons shared between the carbons, they're free to move within the ring. So they're not confined to a particular atom. They are delocalized. Okay? Delocalized mean they can basically go anywhere. They are shared equally between all the carbons within the ring, so they're collectively owned by everybody. And this sounds familiar, doesn't it? This is exactly what electron C is for metals, except this one applies to the ring. 6 electrons, they freely move around the 6 carbons, so equal sharing between all of them. So technically, you don't have a double bond. All right, structurally, there should be 3 double bonds, but that is not what we observe in real life. So as a result, we tend to draw benzene with the hexagon and a circle inside. The circle represents the delocalized electrons that are shared equally. So try not to draw double bonds for benzene. For some of these questions I will show later, I will have the double bonds for benzene because the program I'm using, Marvin Sketch, it's easier to just click and there's a benzene, and I didn't bother find the one with the ring. But know that there are actually no double bonds. It's a special case. So that structure on the bottom is benzene. Let's name some benzenes, okay? Naming aromatics. This is actually quite confusing because you have 2 different conventions for naming the same type of molecule. It depends on the structure, okay? We decide to use one convention over the other. Now, the first convention is benzene is viewed as the parent. That is the backbone, the benzene, with little small branches coming out of it. That's the first convention. How you name that? Well, the same thing as cycloalkanes. Instead of cyclo blah, 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 you just end with benzene, okay? Now, you can use the second convention if you have a really long chain and benzene is on that chain. So it is easier to view benzene as the substituent, the branch, and that long chain as the parent. So when benzene becomes a branch, it's just like methane becoming methyl. Benzene will become phenyl, not benzyl, phenyl. Okay, that is the group name for benzene. Let's look at some examples of this. So the one on top, benzene in the middle with three things sticking out of it. Right, so we should use the first convention for this one because it's much easier to view benzene as the parent. So my question is this: who is carbon number 1? Anyone?
Bromine one, like the one attached to it.
So bromine,
Yeah.
the one that got the bromine. Okay. Any other answers?
The one on the right of the bromine.
The
Yeah.
one on the right of bromine. Okay. Anything else? I heard another one.
I said the one to the right.
Oh, so basically the same answer. Okay. Really? But one student said bromine. 2 students said the one to the right of bromine. Nobody got the right answer. First of all, why did 2 people say to the right of bromine? How is that the first carbon?
It's got to go along the
You have
double bond.
one.
Okay, because you satisfied the smallest double bond, yes.
And you also have bromine at the second.
And then you hook up bromine to be 2. Okay, so number 1 priority, double bond has to have the smallest number, check. Then you satisfy the smallest set of numbers, so bromine's a 2, the methyl's a 3, and then you have a 6. That is the smallest combination, you're right. But I'm saying that's not correct, that's not carbon number 1. See, like I feel like you guys are not listening to me. I just said on this page that there are no double bonds. Okay? Because they're shared equally, they're delocalized, there's no double bonds. And then I go to here. I even told you that in the future questions, I will have double bonds because of my program. It just comes with it. There are actually no double bonds in here. All right, so if there were, then you'd be right. But benzene, remember, those are delocalized electrons. So you ignore the double bonds for the quote-unquote double bond. So that's not carbon 1. So how come the Br1 is wrong then? So why is that one not carbon 1? If that's carbon 1, what would be carbon 2? To the left or to the right? To the left. So that'll be 1, 2, and 5. Okay? That is not the smallest set. 1, 2, 4 is the smallest set. So the parent is benzene. Of these 2, if you choose the methyl on the left to be carbon 1 and you go clockwise, you have 1, 2, 4. If you choose bromine to be 1, you have 1, 2, 5. So you choose the smallest set, it's this one. All right, so again, I told you, when you have a ring, it can be very confusing what is carbon 1. So you have to be very careful. You have to consider all the possibilities, make sure that you have the smallest set and you satisfied everything. So this is 1 methyl, 4 methyl, and 2 bromo. Putting it all together, that would be 2 bromo, 1, 4 dimethylbenzene. All right, sneaky question here. So it all has to do with numbering. So make sure that on the test, you are very careful when you number a ring. The one lower is actually easier. You see a long chain with the benzene on top of that chain in the middle, that kind of look like a bacteriophage. In this case, it is easier to view the benzene as a group, not the parent. The parent is that long chain on the bottom. And it has 7 carbons, and since the benzene is in the middle, it doesn't matter which direction you go. I'm just going to arbitrarily choose that one. You're going to end up on 4 anyway. And that will be heptane. That would be 4 phenyl. Just put that together. You would have 4 phenyl heptane. Okay, make sense, everybody? So which convention you want to use, it depends on the question. Which one is easier for the question? So knowing this, good luck with this one. you have 2 double bonds, a bunch of branches, and 2 phenols. I'll give you around 2 to 3 minutes. This is a hard question, and then I'll take this one up. All right, so this one, you have to first find the parent. It's quite clear what the parent chain is. It has to contain all the double bonds, and it has to be the longest one, so it's got to be that one right there. What do you count from the left or the right? Which one?
Right.
The right. Okay. On the right, you have a double bond at carbon 1. That's it. You should be done with your thinking right there. Because on the left, it starts on 2. So obviously, you take the one on the right. So if you do that, you have to figure out E and Z. But let's label the branches. First of all, that's octo 1,6-diene, right? 8 carbons on carbon 1 and carbon 6. Well, that's a 6-chloro. That would be a 5-chloro. And that's a 7-phenyl. That's a 3-phenyl. And finally, a 4-ethyl. On carbon 1, we don't have EZ. Okay, because, well, it has 2 hydrogens and they're equal, so it doesn't matter. But on carbon 6, we do have EZ. And it is E. Why is it E? Chlorine, that's the high priority group, okay, compared to the carbon, so that one wins. On the other side, the phenyl wins. Okay, that the other carbon only has hydrogen, but that one has a whole benzene on it. So they're on opposite sides, so it's an E. You put it together alphabetically, C before E before P. So it's 6E, 5,6-dichloro, 4-ethyl, 5,7-diphenyl, octa, 1,6-diene. Okay, so this is the name of this monster structure here. The test won't get this complicated, but the naming will still get harder because then you will learn functional groups and all kinds of different variations. But the complexity should not be higher than this. As I know some of you are probably worried. The complexity won't be this complicated, but the difficulty of the rules, yeah, we have more rules to learn. Any questions? All right, so the last thing is reactions of aromatics. Before we get there, let's check these two out. Alkanes. If you have a cycloalkane, your alkane in a ring, you can only do substitution. Okay? How? You lose a hydrogen and you replace that with, let's say, a bromine. So cyclohexane plus bromine, if you have enough heat, then you will make bromocyclohexane and HBr. So you switch the H and the Br. Okay, that is a substitution reaction. We've learned this before. However, if you have an alkene, a double bond, and if it's cyclo, then you will undergo addition reaction. All right, it's addition because you can now break that double bond, have the 2 carbons available to make 2 more bonds, and look, you have a bromine, 2 bromines, so you can just stick 1 on each carbon, and you're done. That is an addition reaction. So you have 1,2-dibromocyclohexane. Okay, alkanes do substitution. Alkenes do addition. Okay, I hope that's clear. What about benzene? Will benzene do substitution or addition? Anyone?
Addition.
Hard decision. Yes?
Addition.
Addition. What is your logic behind choosing addition?
Because there are no double bonds, they're like all tied together.
Yeah, and you chose addition.
Yeah.
I'm not really understanding your thought process here. You're saying that there is actually no double bond, they're all tied up together, So you're choosing addition so you can break them up,
Wait, addition. Oh, never mind.
right?
So substitution is.
Okay, so you're choosing substitution.
Yeah.
Okay, if you choose substitution, you're right. It is actually substitution for the reason that you gave. Because there, in fact, are no double bonds here, if that's crap. It's, in fact, delocalized, and they share all of those electrons as a group. And that is a strong bond right there. That is a society right there, okay? You don't really break that easily. So as a result, benzene, because of its stable structure, it will only make substitution reactions. You don't actually break those fake double bonds, okay? So it will behave like an alkane. A hydrogen on the outside of that ring will be switched with the halogen, and that will be bromobenzene plus HBr. So substitution, not addition. Okay, not addition because you don't have double bonds. Did I make myself clear? All right. This is basically all you need to know regarding reactions of aromatics. Okay, benzenes, they do substitution, not addition, due to their high stability. All right, so this will conclude this lesson. So we learned about triple bonds, alkyne, how to name them, how to draw them. Also, we learned about aromatics, how to name them with 2 different ways, and some reactions of alkynes and aromatics. So do we have any questions? All right, so if not, I'm going to end the lesson.